The purpose of this lab is to be able to calculate the mass of a black hole using the position data of a star orbiting it. By using Newton's universal law of gravitation, I found the black hole's mass to be 5.373 times 10 to the 31st kilograms. To begin with, I had a certain amount of information given to me. I had a data file containing the coordinates of the star as it orbited the black hole, as well as the mass of the star, which was 5.8826 times 10 to the 27th kilograms. The time step between the star's coordinates was 86,400 seconds, which equals 1 day. I also knew that the x position of the black hole was 3 times 10 to the 10th meters, and the y position was -1 times 10 to the 10th meters. To use all this information to find the black hole's mass, I needed to put it into Newton's universal law of gravitation. This law says that the net force due to gravity of an object upon another object is the constant g times the masses of both objects divided by the distance between them squared. When solved for the mass of the black hole, the equation looks like this. I was given all the information for this equation except the mass of the black hole and the force due to gravity. I was able to find both of these values by using v-idle. First, I used my data to find the force upon the star, then I plugged that information into the equation to find the mass of the black hole. I assumed that the force due to gravity is the only force acting upon the star, which makes it the same as F-net. To start coding in v-idle, I made the black hole an object so I could give it properties. Then I began by entering all my initial information: the star's mass, the black hole's position, the time step, and the value of the gravitational constant. The code read the file containing the star's position data so that I didn't have to enter all that information by hand. Next, I used the given information to calculate the net force, as well as the parallel and perpendicular components of the force and the change in momentum. I began with calculating initial velocity by finding the change in the x and y components over the change in time. I multiplied that value by the star's mass to find the initial momentum. I did the same for the following x and y components to find a second velocity and a second momentum. The change in momentum over the change in time has the same value as the net force. I also calculated the parallel and perpendicular components of the net force, even though they are not necessary for finding the black hole's mass. Since I found the net force, I was able to enter Newton's universal law of gravitation into my code and use it to find the mass of the black hole. I chose to make my code print out the mass that it found for every iteration, as well as the time and the net force, so that I could be sure the value stayed the same while everything else was changing, like it should. The mass that v-idle found for the black hole was 5.373 times 10 to the 31st kilograms. This value is confirmed by the WebAssign website. On each iteration of the code, the mass changed very slightly, but never enough to cause concern. Here's what the orbit of the star looks like. As v-idle graphs the data points, it shows 3 arrows representing F-net, F-parallel, and F-perpendicular. The arrow scale value in the code determines the length the arrows should be. Since the forces in this program are so massive, I chose to make my arrow scale 5 times 10 to the -14th, a very small number so that the model and the arrows can all be seen at once. Now, to answer the "what does it mean" question, the values for the force component equal the values for the change in momentum components. So how are they different? Although the values are equal, the meanings are not. The momentum changes because of the forces acting upon the system. F-net causes dp dt. And the what-if question. If the positional data of the star remained the same, could the black hole have a different mass? The answer is no, it couldn't. The given information was plugged into Newton's universal law of gravitation, so the mass of the black hole couldn't be something else unless the given information was incorrect or another force was acting upon the star. To summarize, I was able to find the mass of a black hole by calculating the net force upon a star orbiting it, then plugging that information into Newton's universal law of gravitation. Thank you for watching.